All right, welcome back. So today we are going to be starting our conversation about chapter 4, which is all in regards to linear functions. So the first thing that we need to start is how to identify linear functions. So without further ado, let's begin. So we can identify if a function is linear by looking at its graph, by looking at its ordered pairs, or by looking at its equation. So let's first go and try to identify a linear function from a graph. The first example of your guided notes states the following. Determine whether the graph is a function. Every x value is going to be paired with exactly one y value. So it passes what we called in chapter 3 the vertical line test. Therefore, the graph is going to be a function. So first we need to make sure that every x only has one y, that we are not repeating our x values. If that is the case, we then are going to go proceed to step 2, which is determining whether the graph is a straight line. So our conclusion can be stated for this graph on the right. Because the graph is a function and a straight line, then this graph represents a linear function. And that should make sense. The phrase linear function has the word line in it and, well, function in it. So if we're able to determine that it's a function and able to determine that it's a straight line, well, there you go. We have a linear function. So the graph depicted is a straight line, and again, that is a function because it passes the vertical line test. I want to go through two more quick examples for you. Over on the left, we have an example of a linear function. It passes the vertical line test and it is a straight line. Over on the right, written in red, that is not linear. That is actually what we call a parabola. That's going to be a representation of a quadratic function, which is not going to be linear. And although it may pass the vertical line test, this may be a function, and well, in this case it is, it's not linear. And we can visually tell that because, well, it's just not a straight line. So the first way we can determine if a function is a linear function is by looking at its graph to seeing if it passes the vertical line test. So is it a function? And then, well, is it just a straight line? And in this example, it was. Then we're going to be able to identify using its ordered pairs. So we're given three sets of ordered pairs, 4, 3, 6, 4, and 8, 6. We need to determine whether or not this represents a linear function. The first thing we're going to do is we're going to write those ordered pairs in a table. We're going to create a quick little table with a x column and a y column that is over on the right-hand side, although it's currently covered by my screen shade. Then we're going to find the amount of change in each variable, and we will determine whether that amounts are consistent or if they are not. And in this example, we can say that the x value has a constant change. We're adding 2 each time. So over on the x column, we're adding 2 both times. But over in the y column, to get from 3 to 4, we add 1. To get from 4 to 6, we added 2. That is not constant. So since the y values are not constant, this is not going to represent a linear function because we do not have a constant change. We do not have a constant x change and a constant y change. If we did, then yeah, we would have a linear function. But since in this case, we do not have a constant change in the y values, this is not going to be a linear function. But let's go through two more examples. Over on the left, we have a linear function, and over on the right, we do not have a linear function. And the reason being is if we look at the change in our x, 1 to 5 and 5 to 9, we're adding 4 each time, so that's good. Well, from 4 to 6, we're adding 2. 6 to 8, we're adding 2. So since we have a constant change in our x and a constant change in our y, those may be different, the x and the y changes, but within the x values, we're increasing or decreasing at the same time. And the y values were increasing or decreasing by the same amount. But over on the right-hand side, in the table in red, if we look at our x values, we're increasing by 2. So that is good so far. But if we look at our y values, 4 to 5, we have to add 1. 5 to 8, we have to add 3. That's no bueno. So since we do not have a constant change in our y values, this is not going to be a linear function. Awesome. We have one more way to determine. So we want to determine whether or not y equals 5x minus 2 is going to be a linear function. So there's a lot of different ways to do this. The guided notes start to talk about what is called standard form. And standard form is written in ax plus by is equal to c. Notice that A, B, and C are capital letters because those are what are going to be called the constants or the coefficients. So A and B are the coefficients of our x and y variables. And C is going to be what's called the constant, but those are going to be replaced with numbers. We want to make sure we can change whatever linear function we have into standard form to confirm it's going to be a linear function. Again, A, B, and C stand for numbers. So if we're given y is equal to 5x minus 2, we want to get that into standard form by ax plus by is equal to c. So we're going to subtract 5x on both sides, and there we get negative 5x plus y is equal to negative 2, which is technically in standard form. We're going to be talking a lot about standard form soon. This is just one way to show that a function is going to be linear by looking at its equation. Now, notice in standard form, the exponents have to have a value of 1. So we notice we don't have any exponents because they're all to the power of 1. Notice that x and y are not being multiplied together. We have separate terms with those variables. Negative 5x is one term. Y is another term. They're getting added, they're not getting multiplied. And notice that x and y are not in any denominators. They do not have any exponents, and they do not have any radical signs. Those are three crucial pieces to determine whether or not it's going to be linear or not linear. There's also a lot of other ways to determine it. Let's look at what we have written here. Over on the left in blue, these are two examples of linear functions. Y is equal to 2x, 2x plus 3y is equal to 6. Notice that we do not have any exponents greater than 1. X and y are not getting multiplied together, and x nor y are in denominators. They are not in any exponents, and they do not have any radical signs. So these are going to be what's called linear functions. And we can look at them and simply say, okay, they don't have any exponents. X and y are not getting multiplied together. We don't have any radicals. Our variables are not in the denominators. And we don't have any exponents that have that variable. So these two would be classified as linear functions. So if you saw y equals 2x, you can automatically say that it's going to be linear. But if you look at the right-hand side, I have a couple examples of what are not linear functions. Xy is equal to 4. Well, that's not linear because x and y are getting multiplied together. If I have y is equal to x squared plus 3, that's not linear because we have an exponent that's greater than 1. We have x squared. That exponent has a value of 2, which means this is not going to be linear. We have y is equal to the square root of x. Well, we have a radical, which means that this is not going to be linear. And also we have y is equal to 1 divided by x. And this is also not going to be linear. But a lot of students forget this last example, as it's not going to be linear. We have y is equal to 1 divided by x. And the reason why it's not going to be linear is if I multiply both sides by x, I now get xy is equal to 1. So x times y is equal to 1, which breaks the rule of having x and y multiplied together. So sometimes you don't have to move it into standard form. We will be talking about standard form very soon, but so it's good to be aware of what standard form is, but there are other ways to identify a linear function. So with that, please work on problems 1 through 6 on the guide notes and resume when you're ready to move on. All right, if you're listening to my voice, that means you have worked on those problems in the guide notes and you're ready to move on. So we also have real life problems, and we can talk about the domain and range are sometimes going to be restricted. Let's go through an example together. So we're given this real life scenario. Swimming at a pool costs $2.75 for each person. The total cost is given by f of x, the function evaluated at x, is equal to 2.75x, where x is a number of people going swimming. Graph this function and give its domain and range. The way that we are going to graph it, and so far what we have been able to do is create these input-output tables. when we create these input-output tables, we choose an x value, we plug it in, we see what y value we get, or the function value we get. We then graph it. But now we need to determine the domain and the range. Well, let's think about this in a real life scenario. There's a couple questions that you want to be asking yourself. Can the x value be all fractions or decimals in between those whole numbers? So if you look at the x-axis, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and those represent the amount of people. So can we have fractional people? Can we have decimaled people? Is there any way we can fill in between those whole numbers? Well, can x be 0? Is it possible to x being 0? Can x be negative? These are three important questions that we have to ask ourselves when it comes to real life examples. We need to be able to analyze these real life situations and be able to determine our conclusion. We don't just guess here. We have to actually think about, hey, if this was a real life scenario and I was in this scenario, what would happen? Can the x value be fractional? Can x be 0? Can x be negative? Well, if we're talking about people, well, we can't have fractional people. We can't have decimals in between people. We're talking about people. So it's 1 person, 2 people, 3 people, 4 people. Can it be 0? Yeah. If no one shows up, then it can be 0. But can it be negative? Can we have a negative amount of people? Not quite. So the domain, again, is the number of people. It's restricted to only whole numbers. Because the range is determined by the domain, the money, the cost is determined by the people, that is also going to be restricted. So our domain, the number of people that we can have, is going to be 0, 1, 2, 3, ... so on and so forth. And we don't write an inequality here, because if we said x is greater than or equal to 0, well, then we're including 1 1/2, 2 1/3, and that doesn't work here. So in order for us to show the increasing value of it, we're going to put ... at the end of our bracket. So look, 0, 1, 2, 3, ... showing this pattern continues to go on. And then our range is going to be the values or the cost with those values of people. If we have 0 people, we have $0. We have 1 person, it's $2.75. If it's 2 people, it's $5.50. If it's 3 people, it's $8.25. ... Because this continuous pattern is going to be happening. And we cannot show an inequality because we cannot include that fractional pieces. We only can go up by $2.75 each time because that's determined by our x values, by our domain values. Awesome job. So with this, please work on problems 7 through 9 on the guided notes. Great job, folks. If you have any questions, please jot them down and bring them into class. And like always, have a good one.